So last time we talked about, so we've been talking about these Ehrhart polynomials and Ehrhart series, right? Basically counting lattice points in integer polytopes. And last time I proved Ehrhart reciprocity for you, and that says that if you take the Ehrhart polynomial and you plug in a negative integer into it, which seems like a very strange thing to do, that ends up counting exactly the lattice points in the interior of the polytope. Okay. I wanted to start today by just discussing something very briefly, which is, what if your polytope is not integer? What if it's not a lattice polytope? So can we still say something? Well, let's first talk about the case where P is rational. And when I say P is rational, that basically means that the vertices are rational, have rational coordinates. Okay. And that's equivalent to saying that the inequalities are given by rational numbers. Inequalities are rational, meaning that all the numbers appearing in the inequality are rational numbers. Okay. So what I did here is that I drew for you one of the easiest examples that I could think of a rational polytope that is not an integral polytope. Okay. So this is the origin and the point 1/2, 0 and 0, 1/2. This is P. So what I want us to do real quick is just count the lattice points and the dilates of this thing to see what happens. Okay. So let's do it. P is the convex hull of 0, 0, 1/2, 0, and 0, 1/2. Okay. So, and we're going to count the lattice points in NP. Okay? And first I would like to do it if n is an even integer. Okay? So in that case, NP is going to be, it's going to have coordinates 0, 0. It's going to be the coordinates multiplied by n, which is 2k, right? So this is going to become k, 0, and this is 0, k. Okay? And it's very easy to count the lattice points in here. You know, there's 1 in this level, 2 in this level, 3 in this level, and so on. So the number of lattice points is given by 1 plus 2 plus 3, ... and then the last level has k plus 1 points, right, between 0 and k. Okay. So it's the sum of the numbers from 1 up to k plus 1. And you guys know that's the triangular number k plus 1 times k plus 2 over 2, right? Or in terms of n, we get n over 2 plus 1 times n over 2 plus 2 over 2. Okay? Yeah?
Just a fine point notation. Is the n and the p are switched in that also?
Oh, yeah, thank you.
Just checking, making sure I'm not going.
Yeah, thank you. It's the Ehrhart polynomial of p evaluated at n. It's the number of lattice points. Okay? And that's a polynomial, so this isn't looking too different from what we've seen so far. Okay? We somehow expected this to be a polynomial. Okay? Now let's do it for n equals 2k plus 1. Okay? So what does NP look like? Well, Now, this is a half times 2k plus 1, right? So this means that this vertex has coordinates k plus 1 half comma 0, and this one has coordinates 0 comma k plus 1 half. Okay? But now the thing to realize is that this is not a lattice point because it has y coordinate equal to a half, and in fact the highest lattice point that we have here is 0 comma k, right? And here the last lattice point that we have is k comma 0. Okay? And we have all of these lattice points here. Okay? But then we cannot have any lattice points in this strip because these are all lattice points and this is only a half wide. Okay? And so really the lattice points in here are precisely the lattice points in that picture. Okay? So the lattice points here, it's exactly the same answer, right? Because it's the same thing as before. And but my point is that this is not the same polynomial because k is now n minus 1 over 2, right? So what we get is n minus 1 over 2 plus 1, n minus 1 over 2 plus 2 over 2, or I can write this as n plus 1 times n plus 3 over 4. Okay, and I can write this one as n plus 2 times n plus 4 over 4. Okay? So the point that I want to make with this example is that the story is not too different, but it is different. What we get here is not really a polynomial. It's what's called a quasi-polynomial. And a quasi-polynomial is something that has cases like this, and in each case it's a polynomial. Okay, so here's the theorem for rational polytopes. Theorem, if P is a rational d-polytope, then this thing is a quasi-polynomial and what that means is that there exists a number, let's call it, I don't know, n, such that basically if you want to know what this is, then it's going to depend on the congruence mod n. Okay? So just like here, it depends on whether n is even or odd. Here it's going to be depending on whether you're 0 mod n or n minus 1 mod n. Okay? And for each one of these things, you're going to have a polynomial. Okay? f0 of n up to f sub n minus 1 of n. So there exists a natural number n and polynomials f0 up to fn minus 1 such that we have something like this. Okay? And so, for example, what we did there says that the Ehrhart quasi-polynomial of this thing is n plus 2, n plus 4 over 4 if n is 0 mod 2, and it's n plus 1, n plus 3 over 4 if n is 1 mod 2. Okay? And basically the point is that this works for any rational polytope. Now if you think about it, what is this number n? Where does it come from? Well, it's hard to say precisely, but it clearly has something to do with the fractions that appear in your polytope. Right? You can, I think it sounds believable that because these coordinates were halves, that's why we had to consider mod 2 there, right? So that when we multiply a half times an integer, what happens? Okay. And so the point is that this number capital N that appears there is it's not actually, it's impossible to say precisely what that capital N is, but it is true that it has to do with the denominators that appear in your polytope. That is true. Okay.
There can't be more constituents than there are residue classes of these images, right? You have your denominators.
So basically, if the lowest common denominator of all the fractions that appear there is m, then m is good enough here. Okay. But in general, capital N is a divisor of that m. That's the, I think that's the best precise statement that you can make. That this n divides the lowest common denominator of all your vertices. Okay. So that's the theorem. And by the way, the situation is not very different in the sense that also you have that all of these guys have the right degree. All of these guys have degree D, so that's true. It's true that Ehrhart reciprocity is still satisfied, even though now we don't have even though we don't have polynomials. It's still true that if you plug in minus n here, you're still counting interior lattice points, because the point is that the interior Ehrhart quasi-polynomial also looks like this, and each one of these little things satisfies the Ehrhart polynomiality. Okay. So essentially the same theorems are true. Same theorems are true. And essentially the same proofs work. Okay? I want to give you just one brief indication of the subtlety that appears when you try to pull off the proofs that we've done. Okay? And I should tell you that the details are all in the book, so you can look up the details. But I just want to give you an idea of how the proof changes if your polytope is rational and not integer. Okay. So remember, how did we compute? I mean, how did we prove that the Ehrhart polynomial was really a polynomial? We did it in this. We did it with this lemma that when you consider the generating function, then we got some polynomial divided by 1 minus z to the d plus 1. Remember, that's what we proved. And then you guys proved in the homework that this implies that this is really a polynomial. Okay? And this statement is not true anymore for rational polytopes, but it's almost true. Okay? This we call the Ehrhart series. Okay? And remember that the way we did this was that we said the Ehrhart series at z was, we computed that with the cone, with this cone. And we said that we got this by computing sigma of the cone and then plugging in 1 for all the variables except for z. Okay? And this theorem is still true. Okay? So this is still true. Okay, so this is no longer true, but I'll tell you how to fix it. This is true. Okay? Now, we said that basically the way we did this was by doing it for simplicials and triangulating. Okay? And remember that the way that works is that if P is simplicial, then what we got here was sigma of the fundamental parallelepiped divided by 1 minus z to the generators. U sub d. But we're plugging in 1, 1, 1, 1 z. So actually, you should really be thinking of this as 1 minus taking the vector 1, 1, 1, 1 z and raising it to the u1. And remember then what we said in the previous case is that u1 up to ud are the generators of this cone. Okay? And we said basically what this is doing is that you're plugging in 1 for all the variables except for the last variable. So then what we get when we do this is that we got z to the last coordinate of u1, c to the last coordinate of u2, and up to ud. Okay? And this is exactly where the difference comes in. So if you look at your notes, we said then that u1 was just the vertex of the polytope, comma 1. Right? So for example, this vertex is a vertex of the polytope, and u1 was just taking that vertex and lifting it to height 1. Okay? And so that's why we said that here we got just 1 minus z, 1 minus z, 1 minus z, all these different times, which is where all these 1 minus z's came from. Okay? Actually, we're in dimension d plus 1, so okay. But this is the key. The key is that because this point is not an integer, then when I lift it to height 1, this point is not an integer, so it's not the first lattice point on this ray. Okay? And that's precisely where the trouble comes in. This is u2, and this is u3. Okay? Because these guys are not integers. And so that means that here you're not going to get the trivial exponent 1. You're going to get the exponents to be the heights of these points according to basically the denominator of these vertices. Okay? So for example, in this case, the denominator would be 1 minus z, 1 minus z squared, 1 minus z squared. Okay? So that means that now you don't get something like this. What we get now is something that looks like a product of 1 minus z to the k's. Okay, this kind of thing is what you get. And then basically the point is that what you proved in the homework doesn't apply to this because this doesn't have the right form. Okay? And it turns out that when you have something like this, then what you get is that this is a quasi-polynomial, not a polynomial. Okay? And we've seen series like this. We talked about how what arises here is complex roots of unity and these kinds of things. And that's why complex roots of unity should remind you of things mod k. Okay? This is precisely where the mod k business comes from. It's from the roots of unity. Okay? But so the point is that here we just get, I don't know, some numbers, h1 up to hd plus 1. And that is the complication. So now we get a formula like this, and then if you adapt what you did in the homework to a series like this, then you're going to get that this is a quasi-polynomial, not a polynomial. Okay? So that's just a rough sketch of the proof for rational polytopes. Okay? And I think this is just something to keep in mind in case you end up doing Ehrhart theory. It just so happens that a lot of polytopes that we like, they have integer inequalities. I think in this class we haven't yet seen any polytopes that where the inequalities are not rational numbers. Okay? But integer inequalities means you have rational vertices, not necessarily integer vertices. And so a lot of polytopes in nature are rational polytopes, and so you have to be a little bit more careful. And when that time comes, remember that I told you it's quasi-polynomial, but things work more or less the same way, and then you'll really have to look through this carefully. But this is just a good example to keep in mind of what's the kind of thing that happens. Okay? So that's the first thing that I wanted to tell you today. Maybe the second thing that I'd like to tell you is this, that if you want to study irrational polytopes where the coordinates are no longer rational, then there is no Ehrhart theory. Okay, that's the current state of affairs. And if you would like to develop that theory, you would make a lot of people happy, but that theory doesn't exist. We don't really know how to count lattice points in polytopes that are not rational. That's the current state of things. Okay. So what I want to do for the rest of today is give you a couple of very nice applications of Ehrhart reciprocity. So here's a very nice application. It's an application that maybe some of you know already. It's called Pick's theorem. Pick's theorem is a very nice result, and it says this. It says, let's say that you have a lattice polygon in the plane, and you would like to compute the area. So in general, the way that you would have to do this is kind of cut it up into triangles and sum up the areas of the triangles, and I mean, you can do it that way. But it turns out that there's an easier way, which is this. If you say that I is the number of interior lattice points, and B is the number of boundary lattice points, then the area of the polygon is very simple. Interior points plus boundary points over 2 minus 1. Okay.
This only works in R2, right?
In R2. Have you guys seen this before? No? Do you like it? I like it. I think this is impressive. I think this is an impressive thing. Because again, area we think of as a continuous thing. It's measuring how much water fits in a glass, I don't know. And here you're just counting lattice points. And it basically says something that's kind of intuitive. The area is more or less the number of interior points, but that's not quite right. And it turns out that the correction in the plane is super easy. You just count lattice points, divide by 2, subtract 1. Let me show you. Proof. It's mysterious. I don't have a good reason. I don't have an easy answer for why you get a minus 1, but I can prove it to you. So, and there's many ways of proving this theorem. And I like this one because we already did all the work for this. This is a lattice polygon, so it has an Ehrhart polynomial. So let's say that the Ehrhart polynomial is LP of t. And because this is two-dimensional, this thing has degree 2. Okay? Now, if I plug in 1, then I just get A plus B plus C, right? But what is LP of 1? By definition, this is the number of lattice points in 1 times P. Number of lattice points in P. So that counts I and that counts B. This is I plus B. Okay? Okay. Now let's plug in minus 1. So when you plug in minus 1, you get A minus B plus C. Okay? But what is this at minus 1? Well, it's beautiful. You plug in minus 1 and you get the number of interior lattice points. Okay, so you just get I. Okay? So now let's add these two equations. And we get 2I, it's looking good, 2I plus B equals 2A plus 2c. Okay. Now, remember what we said about the coefficients of Ehrhart polynomials. I told you that I know what the first one is and what the last one is. What did we say? The first one was the area. I mean, the volume, but in this case, it's area. So I get 2 times the area of P. And the last one, we said was 1. And remember why one easy way of seeing that it's 1 is that if you plug in LP of 0, you get C. But LP of 0 is the number of lattice points in 0 times the polytope. And 0 times the polytope is 0, the point 0. So C is 1. So we get 2. So we get this. And that's it. That's the proof. Right? The area of P is I plus V over 2 minus 1. This is the slickest proof that I know of this theorem. There are some prerequisites. You can't just tell this to anybody, but it's nice when you work hard and then you have results that you like as a cheap corollary. Okay. And this is it couldn't be cheaper. We didn't have to work very hard to get this. That's Pick's theorem. Okay. I should say a nice application of Ehrhart. What are we using here? We're using the fact that the Ehrhart polynomial is a polynomial, and we're using reciprocity to say what happens at -1. So we should just say an application of Ehrhart theory. Okay, here's another one. I mean, so. So this is almost what I'm about to tell you. But so that's a great question. The short answer is no. The short answer is that this is a beautiful result in 2 dimensions, and in 3 dimensions it's not as nice. And you want to know about 3 dimensions because you have a homework problem about 3 dimensions, which says, how do you compute an Ehrhart polynomial in 3 dimensions? The point is that in 2 dimensions it's very easy, right? I mean, you get the area like this. You get it very easily like this. I mean, should we? So let's say a little bit more about what I'm saying here. If I ask you to compute the Ehrhart polynomial of a polygon, what would you do? Triangulate, and then write these generating functions, and then would you really do that?
If I could count enough of that area.
I'm sorry? The thing is, I know what A is. I know what C is. So to find the Ehrhart polynomial, I'm only missing B.
Oh, you mean
Of a 2-dimensional, yeah. Of a 2-dimensional one. If I find the area, and that's not hard. Just count. You can find the area of a polygon. You can find 1, and then you just have to find B. So how would you find B? Just count points in the first dilate. This is a number that is very easy to count. Just draw P, count lattice points, and this gives you A plus B plus C. Okay. This is 1. This is the area, so that's easy. This is lattice points in P, and then you have B, and then you have the whole Ehrhart polynomial. So for 2 dimensions, you don't really want to bother with cones or things like this. You just want to do this. Okay. For 3 dimensions, it's kind of it depends a little bit more. Okay. This is a question that is very important to your life this week. How do you find the Ehrhart polynomial of a 3-dimensional polytope? And I told you there's many ways, and this gives us one way, which depending on the polytope might be better or might be worse. Okay. What do you need to compute the Ehrhart polynomial for a 3 polytope? Well, we could try to do a similar thing. It's a little bit more complicated now. We have 4 variables. Okay. But of these 4, this one is very easy because it's a 1. And this one, well, it depends. Can you compute the volume of a 3-dimensional polytope? It's not so easy, but if your polytope is not too bad, then you can do it. And then you have 2 more coefficients to compute. So how would you compute them? Following that idea. So you could count the number of points in P. That'll give you A plus B plus C plus D. And this you can count. Well, I mean, again, it depends on the polytope. If I ask you to count the lattice points in a huge 3-dimensional polytope, it's not that easy, really. But maybe you can do it. Okay. And then what would you do? I mean, that's not enough. You have A, you have D, and now you have B plus C. So then what would you do? So you could compute the points in the second dilate.
You're going to have to take the polytope. Or we could use the
So you could do this, but maybe this is not the best thing you can do. Maybe it's easier to plug in -1. You get minus A plus B minus C plus D. And if you were able to compute the lattice points in P, you can subtract the boundary points. That's not hard. Okay? So then this gives you the number of points in the interior, intersects D to the D. And that means that if you can compute these 4 purple numbers, you have the Ehrhart polynomial. Because this gives you B plus C, and this gives you B minus C, and then you have B and C. Okay? So that's for 3 dimensions. And again, this method, depending on the polytope, is either better or worse. I don't know what your sense is of... I mean, for the polytope that you did in the homework, which one would be better? You think this is better?
Yeah, I think so. I don't know.
I think for your polytope, this might have been easier. You can still do it, by the way. But I did it on purpose. I think once in life one has to compute these things if one is going to understand. If one is going to understand all these theorems that I showed you, I think you had to go through the computation. And this is a good shortcut. Now, if you go to higher dimensions, then it's debatable what's better. But basically, I don't know, if you wanted to do it for a 4-dimensional polytope, then you would have 5 variables, of which the first one would be easy, the last one, well, the volume of a 4-dimensional polytope, maybe you can do it. And then you would need to compute 3 more numbers. So maybe you could compute lattice points in P, the interior of P, and 2P. Or you could compute P, 2P, and 3P if that's easier. And in general, for a d-dimensional polytope, the nice thing is that knowing that it's a polynomial means that you only have to compute d plus 1 values of that polynomial, and you know what the polynomial is. So this is interpolation. And using reciprocity, you can save yourself half of the work, because you can kind of do P and minus P and interior of P at the same time. Okay. There are algorithms to compute these things, and the best one that I am aware of is something called Puntos that was developed by Jesus de Loera at Davis, and I think some other people at Davis. Davis is one of the world's central expert places for computing these kinds of things. But yeah, Puntos, you give it the polytope and it gives you the polynomial. It's beautiful. If your polytope is not too bad, You can do it. But that also brings up a good point. Actually, that brings up a good point, which is that this is not really what you want to do in algorithmically. What you want to do is what we did earlier, okay? But with other tricks. And I think the best available method is something called the Barvinok algorithm. Barvinok is a professor at Michigan. But the point basically is that there's a lot of interesting algorithmic issues here. Okay. Let me show you another nice application. And this is to combinatorics. And this is magic squares. Let's count magic squares. So what is this? Let's define the number Hn of R to be the number of n by n matrices, or let's call them, well, n by n matrices of integers, of natural numbers such that all the row sums are 1, or are R, and all the column sums are R. Okay? So a Sudoku is an example of this. A Sudoku is an example for n equals 9 and R equals 45, I guess. And you guys, I shouldn't have tried to do this on the spot, but you can anyway. You can do this with the numbers from 1 up to 9, so that I know you have to put a 5 in the middle, and that's all I know. And I mean, you can figure it out. This is not hard, but it's possible to make all the row sums equal to 9, all the column sums equal to 9, and to 15. Yeah, better be 15. With the numbers from 1 up to 9, and you can get the diagonals to add up to 9. Also, I'm not requiring this here. Anyway. This is really what people think of it when you tell them magic squares, but we're going to be a little bit more relaxed and call this a magic square also. Okay. So here's a theorem that maybe for you guys won't be surprising at all, but for anybody else it would be, which is that this is a polynomial in R. In R, such that if you plug in -1 or -2 or anything up to n minus 1, you're going to get 0 always. And if you plug in -m for n bigger than or equal to n, then you're going to get Hn of m minus R. Okay. So the first statement is something that I don't think is very intuitive, that this answer is a polynomial in R, no matter what value of n is. And then the second part is even stranger. It says that if you plug in negative numbers into this polynomial, which shouldn't give you anything reasonable, you end up solving the same problem, but for a different row and column sum, except for these places where you can solve it. Well, maybe you don't see immediately how to prove this, but you can believe that this is related to what we're doing, because it's the same kind of thing. We have this polynomial, and we're plugging in these weird values. Okay. So why is this a polynomial? Well, maybe it's just an Ehrhart polynomial of something, right? That's what we would like to do. And it turns out that this is the Ehrhart polynomial of a polytope that you guys are familiar with. Because this is exactly the polytope of that matching service problem. So It's called the Birkhoff polytope. It's the convex hull of all m by n permutation matrices. And this is in r to the n squared. But you see, and maybe this, I mean, this is not something that, this is something that you might not be used to, but I'm going to take r to the n squared and I'm going to write my vectors. Instead of writing them as a column of length n squared, which is what we've been doing, it's going to be more useful to write my vectors as a square array. Okay, and I'm going to call that a vector, and you can't stop me because I can. I mean, what do I need? I need to be able to add these things. If I want a vector space, I just need to be able to add these things. And if you add m by n tables, you get m by n tables. And you need to be able to multiply by scalars. And if you take an m by n table, you multiply by a scalar, you get an m by n table. So my vectors are going to be tables. Okay. It's not so strange when you get used to it. And by the way, the connection with this dating service polytope is that one of the vertices of this polytope is something like this. So this is the permutation matrix, exactly one in each row and column. Okay. And then you should think that these are the men 1, 2, 3, and 4. These are the women A, B, C, and D. And this exactly corresponds to matching up dates between 2 and A, 1 and B, 3 and C, and 4 and D. Okay. So this is so the vertices of this polytope exactly correspond to the possible ways that you can match up n men and n women. Okay. So in that problem, I asked you to compute the inequality description of that polytope. And let's say what it is. This is where you see it actually. This is kind of hard to do if you don't write them in this way. So Bn consists of the vectors in R to the m by n, satisfying the following conditions. Well, one condition that is satisfied by any one of these permutation matrices is that in every row, the sum is equal to 1. So if I take sum from I equals 1 to n, or I should say I is a row, so I'm adding up over the j's. This is the sum of the ith row, and we know that for any permutation matrix, the ith row contains exactly 1, 1, and all the rest are zeros, so I have this. Same thing for the columns. So if I add up the numbers in column J, I should also get 1. Okay. And so far I have no inequalities, and I'm trying to define a polytope. But it's also true that for any of these permutation matrices, all the variables are greater than or equal to 0. So I think it's very easy to see that every permutation matrix satisfies these three properties, which means that the convex hull of these vertices is contained in this inequality polytope, in this H polytope. But it turns out that actually this is it. This exactly describes the polytope. This is the H description of the polytope. Okay? And this is great. This should make you think of magic sums, right? Magic squares. Okay? What happens if I take R times this? If I take R times this, then that is going to multiply this by R, this by R, and this by R, but that doesn't change anything. Okay? And so I have the condition that the row sums are R, and the column sums are R, and the numbers are non-negative. And that means that if I take a lattice point in this polytope, what am I doing here? Well, lattice point means that all the coordinates are integers. So I'm saying put integers in a table, make sure that the rows add up to R, the columns add up to R, and the numbers are non-negative. And so this is exactly the solutions to that problem. So this is exactly the set of magic squares that we're looking for. With that value of R and N. And that means that if I take the Ehrhart polynomial evaluated at R, that exactly counts lattice points here, and that means that it exactly counts the solutions to that problem. Okay? So this is exactly Hn of R. Okay? So this is very pretty, and I think what's most interesting about it is that I think historically it was the other way around. So people were studying this enumerative problem, but then somehow if you think of the right polytope, then this is an obvious statement when you know Ehrhart theory. What is the only thing we need to check? That the vertices are lattice points, but they're integers, right? The vertices are R times these things. So this is just Ehrhart's theorem that this is a polynomial, and presumably this is going to be Ehrhart reciprocity, right? Because what else could it be? So let's see why. What happens if you plug in minus m? Then Ehrhart theory tells you what happens. By the way, one thing I didn't tell you is that this is a polynomial of degree n minus 1 squared. And the reason for that is that this polynomial, this polytope, has dimension n minus 1 squared. And I think I also asked you to prove that in the homework, did I? Can't remember. But it's not hard to see because you have n squared variables minus n equations, n squared minus n, minus n other equations, n squared minus 2n. But then the sum of these equations is equal to the sum of these equations, meaning that you have one non-equation, so n squared minus 2n plus 1. It's kind of a quick argument for that. So Ehrhart theory tells you that when you plug in minus m, you are just counting points in the lattice points in the interior of m times this guy. Okay? But if you think about it, what are the interior lattice points here? They are the number of arrays with row sums and column sums equal to R. But the only thing is that now you have to be interior, so you're not allowed to be 0. So you're not allowed to put zeros in the array. So you have to put positive integers because you're not allowed to put a 0. Okay? And then I'm going to do this trick where I'm going to say, well, if you force me to put all of these numbers to be bigger than 1, to be 1 or more, then let me just subtract 1 from each one of these numbers. And then what I'm going to get is a solution to the old problem, except that now the sums are going to be R minus N. Okay? So what you get is the number of arrays with row sums equal column sums equals R minus N. And what I get from here to here is I just subtract 1 to each entry. So then instead of getting positive integers, I get non-negative integers. And instead of things adding up to R, they add up to R minus N. Looks like I mixed up my M and my R. So this is M, 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 M. Okay? And so this is exactly H sub N of M minus N. And that shows that actually I had a typo here. This should be N minus N. Okay? So that proves this. And then finally what I want to say is that if you look at these values where M is between 1 and N minus 1, then it's impossible to form an array of positive integers where the row sums and column sums are between 1 and N minus 1, because you have to add up N numbers. They're all positive, so they're going to add up to at least N. Okay? So that means that this cannot be done for values less than 0.